Welcome to lecture 17. We are studying basic electrical engineering. In last lecture, we studied Thevenin's theorem and went through the step to apply Thevenin's theorem on a circuit to find unknown quantities. Today, we'll solve a circuit for an unknown quantity where we have both dependent and independent sources. The technique is a bit different than the technique we apply when we have all independent sources. For this, the first step is the same. We'll remove the load. We have a 6 kilo ohm load across which we have to find the output voltage. The first step is the same, that we remove the load and find open circuit voltage across it. To find this open circuit voltage VOC, we can either use loop analysis or nodal analysis. If we use node analysis, we'll assume a voltage here at this node which is equal to VOC because the same node. So let's write KVL equation, apply nodal analysis and write KVL equation for this node. That is VOC minus 12 over 4K is the current plus VOC the downward current is VOC minus Vx by 2 divided by 4K plus the current in this branch is 0 is equal to 0. So here we have one equation and two variables VOC and Vx. We can simplify this because we have 4K in denominator on both sides, so we can get rid of 4K straight away. So the equation becomes this. So now we have, or it can either be written as 2 VOC plus VOC, 2 VOC plus Vx by 2 is equal to 12, or multiplying both sides by 2, this becomes 4. Since 2, this becomes 24. So now we have one equation and two variables. So in order to solve for VOC, we need one more equation. So here on this circuit, we see that Vx is the voltage drop across this resistor, which is 12 minus the voltage at the left end of this 4K resistor is 12 volts, and to the right, and voltage on the right side is VOC. So the voltage drop is 12 minus VOC. So Vx is the voltage drop across resistor, which is 12 minus VOC. Now we have two equations and two variables. We can plug the value of Vx here, which is 12 minus VOC, and find VOC. Three VOC is equal to 12, or VOC is equal to 4 volts. Since VOC is also the Thevenin volt, Thevenin, one of our required quantities. Unlike the circuit where we have all independent sources, when we have at least one dependent source, we need to apply a different technique to find our Thevenin. We cannot find our Thevenin straight away because we don't know the internal resistance of this source. So instead of finding our Thevenin at open ends, we make this short and find this I short. To find this I short, we can apply node analysis or loop analysis. Let's apply loop analysis here. Assume a current I1 for this loop and I2 for this loop. Let's write KVL equation for loop number 1. We'll write it minus 12. Why minus? Because the current is entering from the negative side, its voltage rise, and as per our convention we write it negative plus 4k I1. Through this 4k resistor we have only I1 current flowing, plus this 4k I1 minus I2 is equal to 0. Oh, no. Minus Vx by 2 is equal to 0. So through this 4k resistor we have two currents, I1 minus I2. The net current is I1 minus I2 when we are in this loop, minus its also a voltage rise, therefore minus Vx by 2. So this is equation number 1. We can see we have three variables here, I1, I2 and Vx. So we need two more equations to find I1, I2 and Vx, and we are interested in I2 because the I2 is the same as I short circuit. So let's write equation for the second loop, plus Vx by 2, because the current enters from the positive side, so voltage drop, we write it as positive, plus 4k I2 minus I1. The net current in this loop is I2 minus I1, and that's all. Is equal to 0. So this is our equation number 2 to find I short circuit. So we need one more equation so that we can find all the unknowns, and that would be in terms of Vx, because Vx is the voltage across this 4 kilo ohm in this direction, the direction of I1. 4k I1 is Vx. So by solving these three equations we can find I1, I2 and Vx. I have solved this in my notes, and I2 comes out to be 3 by 2 milliamperes. By solving these three equations simultaneously, I2 comes out to be 3 by 2 milliamperes, which is also ISC, I short circuit. SH, I short. We write it as I short. Then our Thevenin is computed as V open circuit over I short circuit. V open circuit, we computed V open circuit to be 4 volts over I short circuit is 3 by 2 milli. So this is 4, 8 by 3 kilo ohms. So now we have computed V Thevenin, which is VOC, and R Thevenin, and now we are ready to apply to build the model, the Thevenin's equivalent model. So what is the equivalent model? The equivalent model contains a source which is equal to V Thevenin, 4 volt in this case, a resistor R Thevenin which is equal to 8 by 3 kilo ohms, and in series with the resistor RL, which we removed in the first step, which was 6 kilo ohms, and the voltage drop across it is our desired voltage. So to find this voltage, we can straight away apply voltage divider theorem. So V out can be computed 6k in numerator divided by the sum of the two in denominator times the applied voltage 4 volts. So solving this yields V out to be equal to 36 over 13 volts. In the upcoming lectures, we'll solve problems related to the sister theorem of Thevenin's theorem. We call it Norton's theorem.